Today we are going to see the application of linear differential equation of second and higher orders. The bending of beams under given loadings can be investigated with the help of differential equation with some assumptions. Assumption 1, the beam is of uniform cross section with its axis horizontal and its width and depth are small compared to its length. The axis of the beam is a line through the center of gravity of the cross section. Plane section of the beam perpendicular to the axis remain planes after bending, while fibers parallel to the axis are bent into curve which are perpendicular to those planes. Point 3, the beam is perfectly elastic so that Hooke's law is obeyed. Thus, stress per unit of any fiber of the beam is proportional to the stretch per unit length. That is, tension in any fiber cross-sectional area of fiber, that is equal to E into extension divided by original length. Where E is Young's modulus for the material. Fourth point, the bending is in one plane and taken to be so small that a simplified formula is used for radius of curvature of the beam at any point. So radius of curvature capital R is equal to 1 plus dy by dx the whole squared, the whole power 3 by 2 whole divided by d squared y by dx squared. For small bending, dy by dx is small. Therefore, dy by dx the whole square may be neglected. Therefore, r is equal to 1 divided by d squared y by dx squared. The surface containing such fibers is called natural surface. Neutral of the beam. The curve of any particular fiber in the surface is known as the elastic curve of beam. Or deflection curve. The line in which any plane cross section of the beam cut the neutral surface is called the neutral axis of that section. The sum of the moments of the force about neutral axis is E into I by R. E, already we know that Young's modulus. Capital R, we know that curvature, radius of curvature, and I is moment of inertia. Of the cross section area of the beam. So considering the equilibrium of any cross section of the beam, the internal moment EI by R due to structure of the beam must balance the external moment due to the various load acting on the beam. Hence EI by R, that is equal to M. M is called the bending moment. Now as explained, when the deflection is very small, capital R is equal to 1 by d squared y by dx squared. Therefore, EI into d squared y by dx squared is equal to M. This relation is known as Bernoulli-Euler formula. The product EA is called fluxural rigidity of the beam. Example, a horizontal beam of length 2L with a uniform load omega per unit length is freely supported at both ends. Find the equation of its elastic curve and its maximum deflection if the load is omega per unit length. A horizontal beam of length 2L with uniform load omega per unit length is freely supported. So solution, this one is take coordinate axis. So axis. So midpoint x equal to L because the horizontal beam of length 2L. Let P be any point on the elastic curve. P any point of the elastic curve. The total weight supported is 2L into omega. Hence, the upward thrust of the support at each end L omega. So the each end is L omega. So this one is L omega. Straight line. Let's assume A. Consider the segment OP of the beam. So let's take OP of the beam. Consider the segment the force acting in this region are upward thrust omega L at O. That means omega L at O. Here also omega L at these two ends. And load omega acting at the middle of OP. So here the load omega x and load omega x acting at the midpoint of OP. Then EI into d squared y by dx squared is equal to m. But m is algebraic sum of the moments of the external force acting in the region OP. So here the external moments, this one omega x downward and this omega L upward into x. So this part x by 2, this one is x equal to L midpoint. So that is equal to the algebraic sum. So omega x into 1 by 2 into x. This minus upward direction omega x into L. That is equal to EI into d squared y by dx squared equal to omega into x squared by 2 minus omega L into x. Here, this one omega L x direction and the point P omega x acting the midpoint of OP. So this is the omega L by 2 the boundary condition y is equal to 0 when x equal to 0. So this end there is no bending of beams. and y is equal to 0 when x equal to 2l. So both end y is equal to 0. Now integrating this equation, let us equation number 1, ei integration, so d squared y by dx squared, that is dy by dx, that is equal to omega integration of x squared is x cube by 3 into 2 6 minus omega l into x squared by 2 plus sum a. Now again integrate with respect to x, we can get y. So again integrate y is equal to omega x power 4 by 4 into 6, so 24 minus omega l x cube by this ax plus b. So substitute the boundary condition y is equal to 0 when y is equal to 0 when x equal to 0. So that means this one equal to 0, x equal to 0, this time 0, a into 0 0, so b equal to 0. Now apply the second boundary condition y is equal to 0. So now this case y is equal to 0 when x equal to 2l. So this one 0 equal to omega by 24 2l the whole power 4 minus omega l by 6 2l the whole power 3 plus a into 2l, b equal to 0. So that is equal to, now we have to find out the value of a, 2al that is equal to 4 to power 4 by 24, that is 4 omega by 24 into 16 omega by 24 into 16 l power 4 minus omega l by 6 into 8 l power 3 plus 2al. Therefore 2al equal to, therefore 2al is equal to 4 omega l power 4 by 3 minus 2 omega l power 4 by 3. That is equal to 1 by 3 omega l cube. So b is equal to 0 and a is equal to 1 by 3 omega l cube. So the equation e into I into y equal to omega x power 4 by 24 minus 1 by 6 omega l x power 3. The value of a is 1 by 3 omega l cube into x. The maximum deflection of the beam is at its midpoint. Therefore y maximum, that is equal to a midpoint, that is equal to the x equal to l, because length of the x is 2l. So put x equal to l, omega l power 4 by 24 minus 1 by 6 omega l power 4 plus 1 by 3 omega l power 4. So maximum deflection that is equal to 5 by 24 into omega L power 4. Hence, maximum deflection is 15, 15 by 24 omega L power 4 into EI. So Ymax equal to maximum, that is equal to 15 omega L power 4 by 24 into E into I, Young's modulus into